Okay, welcome. So today the lecture is on abduction or abductive inference. And this is a form of reasoning that is considered the third form of reasoning from deduction and induction. And to give you a feel for how it's different is abduction is like solving a mystery. You have a bunch of pieces of evidence that you have observed after the action took place. And you need to figure out what caused that to happen. So if you play the game Clue, you're looking at the butler did it, or the old lady did it, or whatever. That is your explanation. That is what you are trying to abduce. Now, you could imagine playing the game Clue, and let's say that we give you a variance where maybe there's a bunch of missing pieces or a bunch of duplicate pieces. And for a given instance of your mystery game, there could be more than one possible culprit that you could conclude with equal likelihood. With abduction, you can have multiple solutions. And I actually misspoke using the word likelihood, because if you're doing things in a probabilistic sense, you could still have a deductive inference. But what I'm saying here is there could be multiple solutions to the same abductive problem. And in many cases, it could be like exponential or infinite. For deduction, you're typically going to have one solution. Maybe that solution is over a probability distribution, but you're generally going to have one solution. And so let's take a look at this a little bit closer. Inferring the best possible explanation for a set of facts. This is probably the simplest way to put it. And as I already stated, that this is earlier work. Give you the foundations of what this means. I remember when I took my first teaching job before I came here, I had a bunch of papers on abduction from my dissertation. And someone asked me if I was doing work on like kidnapping or something. And so, it was really great that now, because there's been a little bit of a resurgence in this way of thinking, like I actually go to places and I say I do abduction and usually there's like one or two people in the room who thinks that's cool. And it used to be zero. So that's like an infinite improvement right there. America's greatest logician, according to Bernard Russell, Charles Sanders Peirce, is the guy who came up with this idea. And the key thing he noticed is that this is a different form of inference, and we'll get into why. He's also known for significant contributions, particularly to quantifiers. And he actually came up with some of the, very early on with the way we think of quantification and logic today. So in order to understand abduction, a nice way to think about it is how does it compare with induction and deduction? So we set this up in a way where you have a case, so your base facts, and then the model, and then the result. So you can think of a real simple thing is, x plus y equals z. And if that is my model, and if my base facts are 2 and 3, my result is 5, okay? That's actually a really good example because if I have 2 and 3, I can deduce 5, I'm always gonna deduce 5. But if you give me 5 and that x plus y equals z, you can come up with something like 1 and 4. So here's another example written in first order logic. We have teaching, me in this class. And then we could have some logical rules. Say, if someone is teaching CSE 598, that person works in the computer science department. Likewise, we could have, if someone's teaching 571, that person also works in the computer science department. And here we have a result that I work at the computer science department. Okay? So deduction, this is the input, the case and the model. So clearly, if I'm teaching CSE 598, this rule fires, and we get that. And that is the output, the results. And so again, solving a math problem. Let's say you train a policy for reinforcement learning and then executing that policy in a game, that is also kind of a deductive sort of thing. So what about induction? Well, here's what we get. We got the case and we got work set, and we want to induce the model. So there's our output. Now you see in this particular example is kind of interesting because that second rule we can't induce because I didn't give you enough training data to come up with it. And that's very telling because, of course, supervised learning and inductive logic programming, these are like kind of prime examples of doing induction. You're coming up with a model. And of course, you can see, shortcomings of it. It really depends on, what you have here and here drives what you have in there, and so forth. Okay, so abduction is the only thing that's left. This is the input. You have the model and you have the result, and now you want to find those initial conditions. Okay, so here's our output. And so medical diagnosis, classic abduction problem. A lot of research done on that, especially in the 80s and 90s. And like I said at the beginning, solving a mystery. That's an abduction problem. Okay, so let's take a look at this again. Here is from the last slide. We have the input, which is the model and the result, and then we can abduce this case. Now, with induction, you have a set of hypotheses, an additional piece of your input. And this is sort of the area in which you can pick out potential solutions. So I just gave a few ground atoms here. We got, I'm teaching 598. Here I'm teaching 571. This one is me owning a car, okay? And so if I'm given these hypotheses, you can pick one. In CSE 598, teaching that is one of them. We can come up with that conclusion. But as you can see, and before I get into that, in abduction terms, the result is called the observation because it's what you observe. We will call the model the theory, and the case the explanation. Okay, this is what we're going to explain, this set of observations based on this theory. Now, given all that, we could have multiple solutions. So here, based on the same input, I can also conclude I'm teaching CSE 571. Okay, there's no other information there. There's another explanation. I can be teaching both. Okay, that's still a valid explanation. And so this raises a big question. How do we decide which one to pick? So there's really two requirements for an explanation, and they are covering and parsimony. Covering means that all observations need to be explained by the explanation. So we saw in the previous slide, there was an atom owning a car. And if I pick that as my explanation, it would not cover any of the observations because none of the rules would fire as a result. Parsimony means that the explanation must meet some standard of simplicity. And this is being intentionally vague here because there's many ways that you can do this. And we'll go over some very straightforward ways and see how that can build up and become things more complicated. All right, so here's the same problem again. H, the set of hypotheses that we can pick from, O, the observation, and T, the theory. All right, so covering. So this clearly is covering. This was the answer we gave earlier. And likewise, this explanation that includes all the hypotheses is also covering. And as I said, if we pick the one where I'm owning a car, it doesn't cover any of the observations. Likewise, the empty set could also be an explanation here, though it's not covering in this problem either. All right, so parsimony, there's a few different ways. And by the way, there is a paper called the Complexity of Logic-Based Deduction that I posted on Canvas. It has a whole bunch of stuff proving complexity results in various types of logical abduction problems. But the real reason I put it in today's lesson is it has an extremely succinct and formal description of abduction problems that's worth a read. It's not too hard to get. And so I based some of these slides off of that. So anyway, with the kind of abduction problem that we've shown you so far, you have what's called irredundancy or subset minimality. And what that means is there is no subset of my explanation that is also an explanation. The second one is minimum cardinality, and that's pretty clear. This is a common thing for those of you who get combinatorics, get the smallest set possible that's still covered. Prioritization. Now here we might maybe have additional information where the hypotheses are grouped according to some kind of priority. And I will use some of them in an explanation first over others. And finally, penalization. Maybe I have weights for the hypotheses and I get penalized by having some function over those weights be higher. So I want to maybe minimize that as well. Yes?
Isn't minimal cardinality also similar to irredundancy?
No, and we'll show you why. So parsimony, let's talk about irredundancy. So here was the first thing we did. Now clearly this is irredundant because the empty set is not a solution. That's the only subset to that. But this is not irredundant because it has additional elements, and I can take the first one as a subset of that, and it is, so therefore it's not irredundant. Now, where I could have something different is, let's say I had a rule that was me teaching CSE 598 and CSE 475 in parentheses, or CSE 571. In this case, I could have a set of two hypotheses and an explanation, because it would require me to teach both due to the conjunction. But there would also be a smaller size solution. Both would be irredundant. The first one would not be minimal cardinality. Here's another example of one that does not meet the irredundancy requirements. And then minimal cardinality. So clearly anything that was the size of 1, and this does not meet that requirement. Did that answer your question?
Yeah.
Okay. Okay, so there are some ideas relating to this. So if you have a space of hypotheses, and as we talked about, there can be very many different explanations. And so we may want to just evaluate the individual hypotheses by themselves. So a hypothesis is relevant if it's in at least one explanation. So for our toy problem we had, me owning a car is not relevant because it never comes up in the theory. So this one is relevant, this one is not relevant. Now, even if I had owning a car in the theory, but maybe if it was disjunctive or to a given body of a rule, there could be times when it's still in the theory, but it's also still not relevant to the ultimate outcome. Necessary is the other case wherein all of the solutions to the abduction problem, that hypothesis must occur. Now, in our toy example, we don't have anything like that because we can switch between me teaching CSE 598 and me teaching the other course as an explanation. Now, if I had this conjuncted to all rule bodies, this would then become necessary. So a couple different types of abduction. So we've been talking right now about logic-based abduction. And that's because, this is kind of a nice way to start. We can express things and look at rules and understand why. A second type is called abduction by set covering. And this is perhaps the most simple type of abductive problem where the problem reduces directly to the set covering or similar combinatorial problem. Probabilistic abduction, where now we're assigning probabilities to hypotheses. And the last one, consistency-based diagnosis. So we'll talk about each of these a little bit. So logic-based abduction is the most general of what we described here. In the Eider-Gottlob paper that I included on the lesson plan today, they describe it with a first order logic, but there's been other research that uses things like probabilistic or annotative logic that allows you to bring in, elements of uncertainty as well. So this is the most general, this approach, I think for the obvious reasons, but also it ends up being the most computationally expensive. So the Eider-Gottlob paper is really just one big negative result. Most everything in there is, harder than, the complexity class NP. Now, ways to make it easier is the types of logical sentences you allow in the theory. So in our simple example today, that's a very easy problem to solve because I have only rules and the body of the rule has no negation in it. So actually the problem I showed you reduces directly to the set covering version of abduction. So we can see all kinds of different ways we can restrict the syntax of the language to make things easier from an abduction standpoint. The other thing is the type of parsimony requirements. So for example, if I only need to find one explanation and it just needs to be irredundant, that's generally going to be easier than if it needs to be minimum cardinality. If I need to do something where I start to have to enumerate explanations, I go up the complexity hierarchy fairly rapidly. In fact, even with abduction by set covering, counting the number of solutions to the abduction problem is generally going to be sharp P hard. So abduction by set covering, we have a set of hypotheses that's atomic, kind of like in the example that we've been going through. And the theory is really just a simple mapping between the hypotheses and potential observations. And so because of that, you have kind of this bipartite graph structure. You can now start to map it to various combinatorial problems, set covering, max K cover, weighted variance, and so forth. And we'll talk a bit more about this a little bit later in the lecture. One thing though, I do want to say is that with these combinatorial problems, they have been studied for a very long time. And there's a lot of really great implementations for solving this type of optimization problem. Although it's simple, you can get really good solutions, and this works great if you have something that's very domain specific. So probabilistic abduction, and we'll talk about this one as well. But we can think of this in terms of conditional probabilities. We want to abduce a set of hypotheses such that the probability of those hypotheses being true, conditioned on the observations, is maximized. And so 3 conditions Eider and Gottlob give where this is useful is there is a structural relationship between the hypotheses and the observations, and that can be simply expressed in something like a Bayesian network. Probabilistic knowledge is available, so of course you have to have that is, I think, straightforward. And then the other thing is typical assumptions for your probabilistic framework can be made. So you have to know what things are, where the dependencies are, basically, and which things are independent. So consistency-based diagnosis is a little bit different approach. And here you have a theory that in this line of work has been called a system description. And H represents components of the system. And I'm going to express this using logic by introducing a special predicate called ab for abnormal. And a diagnosis set, or an explanation here, is a set of components, so a subset of H, that are behaving abnormally. So if the system is operating normally, the theory unioned with the observations, unioned with the negation of abnormalcy for each of the hypotheses, that must be consistent if everything is going well. But again, the whole reason that you want to do this, you have the system description, and you observe things going wrong with this very complicated system, and you want to abduce which components are. So if O has some things that are abnormal in the behavior, we then want to abduce an explanation that looks like this. We have some of the hypotheses are abduced to be the negation of abnormal, and then the rest in set A are abduced to be abnormal. Yeah?
Can we say that this is like a subset of logic-based abduction?
The way I'm expressing it, yeah. And actually the Eider-Gottlob paper does talk about the equivalences between the difference in framing, and this is actually kind of an important takeaway, so I'm glad you asked that question, is what algorithms enable you to do the work. So with the set covering, it's the combinatorial algorithms. With the way, with the probabilistic stuff, probably going to be some kind of Bayesian reasoning, assuming that you're framing it that way. Here, we can leverage work on identifying inconsistencies in a logic program. Because by doing that, we're looking to see how can we go from the top one, if O has any, non-functional operations in it, we want to transform it from the top to the bottom by removing the negation of some of the abnormal things. So there is, getting to your point, there is work that shows that for variants of this, there's equivalences in both logic and the set covering version. And we are going to talk more about this next week when we get into ABL, which does this approach, but in kind of a novel way. All right, so I'm going to walk you through in detail some of my work from a while back where we use the set covering approach for what we call geospatial abduction. Now, in the first paper where we introduced this concept, we kept it very simple. And then later on, we started extending it, and we did things like looking at dependencies and probabilistic stuff and so on. But I think this is kind of a nice way to make some of these ideas concrete with respect to the set covering variant, as well as describe how we went about solving it. So anyway, in this work, we called the hypotheses partners. And so the inspiration from it came actually from an intelligence technique. And the idea is that here we have a bunch of IED attacks. These are like roadside bombs. And maybe just by looking at some stats of the data, we know that for the most part, these bombs are going to be located anywhere from half a kilometer to 2 kilometers away from where they're storing these munitions. And the idea is that if you see where all these attacks are occurring, the bad guys, they can't be storing their munitions, hiding them somewhere too close, because right after the attack happens, everyone wants to search there, police or the military. But if it's too far, then they're going to risk getting caught in transit. And so we just use some hard constraints in this problem later where, we soften it to PDFs over the distance. But let's just kind of stick with the hard constraints for now. And so we were able to use this, we created this software called Scare based off this research, and we were able to find cache locations that were within about half a kilometer away from the actual the ground truth. And again, this is done with no supervised training. The only bit of data we had historically was the distances between the where the attack happened and where the weapons were stored. But that could also come from domain knowledge. So how do we set this up? Well, we had space. So we just did a discrete grid over the geographic area. We had this thing called the feasibility predicate that was a function that took locations in the space and just maps it to true or false. So very simple. Again, we would say it's false if the location was like in the water, or if it was in a neighborhood that wasn't friendly to the people planning the roadside bombs. So we have that bit of information, and then we have distance constraints, and then the explanation is a subset of the space that are where everything in the observation set has a partner or hypothesis. So because we were taking the combinatorial route, we framed this as a combinatorial problem. And the decision variant we called K-SEP, the K-spatial explanation problem. So given that input, the space, the observations, the alpha beta distance constraints, and the feasibility predicate, find the set. And this is NP hard from a computational geometry problem. And so if you want to do exact solution, it's really easy to come up with some enumeration approach. But of course, we can do better by framing it as a set covering problem. Because what we're showing here, so this is a sample map from the paper in one of the examples. The blacked out area are things that were not feasible. The crisscross lines, of course, are the grids, and we have the O's are the observations, and these concentric circles are the alpha and beta distance parameters. So you can see by looking at it, we could probably guess, hey, some of these places of high overlap, are likely candidates for a minimal size explanation. And that's exactly the kind of intuition that we have. We treat the observations as subsets of the hypotheses in this case, because we say set O is associated with everything within those distances. Set O2 is just associated with these two here, and so forth. So because of that, to find a set of a certain size, we can then directly use combinatorial algorithms. Now, what we did in the paper is we came up with some clever ways based on kind of the structure of the space and so on, where we could have like further efficiencies in that. But at the end of the day, they were still all combinatorial algorithms with approximation ratios and stuff like that. And so, yeah, the greedy approach for this, of course, at each iteration, select an observation, then select a partner point for that observation that covers the most observations that haven't been covered yet. So that's like the simplest way to do this. So we implemented this, and the reason I included this implementation slide is Abduction is usually very explainable. Set covering abduction is going to always be explainable. And so when the system produced a set of partner points and says, I think these are the locations where the bombs are hidden, we could click on that point and it says, hey, these are the associated observations. You get that for free. You know that, the algorithm knows that while it's doing that greedy selection. So this is actually a really nice aspect of this to keep in mind. So what are the shortcomings? Well, the approach like this is going to select partners or hypotheses just to do covering. It's prioritizing covering. And if it has something in that kind of intersection with all the points that I was pointing out in the last slide, it's going to go for that, even if those points are maybe not very likely for some reason. It doesn't have that additional information. Now, in our deterministic approach, we overcame some of that with the feasibility predicate, but still, that's still very coarse and limited. Also, it might be the case that the most probable explanation doesn't have minimum cardinality. Minimum cardinality is a little bit of an artificial thing to optimize for, I believe. Because you maybe have, say, two different groups planning bombs, and two of the bomb locations in the middle just happen to coincide a bit, but you want them separated out. And the other thing is, if you do have that data, maybe you're not using it as much as you can. Maybe some of that data we can use to, get probabilities over things. And so I talked about how we just kind of, came up with those distance parameters as sort of very hard things from looking at the data. But obviously that's, not very informative. I mean, right away you should be thinking, well, why can't we have a PDF over those distances? In later work, we actually did that. So the next thing I'll cover is a probabilistic variant. So I'm going to talk about something that combines logic and probabilities together. And it's written by David Poole. It's called Probabilistic Horn Abduction. And it makes a limited number of probability kind of assumptions about mutual exclusivity and independence. What's interesting about this is the propositional case of this form of logic abduction with probabilities. The propositional case is equivalent to a Bayesian network. But by having it in a first order logic, you actually get a lot more expressivity. It's more expressive. Okay, so here's the basic scenario. So let's say we have some inverters, okay? And the inverters are inverting signals, and that we have value at PVT means that port V has a certain value at time T. In is the input port of gate G, out is the output port. And OK means it's working, shorted means that it's shorting, and blown means that it's always going to have an output value of off. So, for example, if we have a signal that's going through an inverter and it's a positive signal and the inverter's blown, we don't know if that inverter is working or not because it always is returning off. So, how do we capture probabilities? Well, they have what is called this disjoint declaration, which is a set of atoms, so non-ground, so it could be specified anywhere. But the variable is shared. And each atom is associated with a scalar that sum to 1. So here, the first one is the gate is either OK with a prior of 0.95, it's shorted, or it's blown. And then we have a second one about, the value associated on the, or we have about the status of the gate, if it's on or off. So we have that 50 thing. So here, the observation could be expressed in the first order logic formula. We just observe what has happened. Because again, remember, if that gate is blown, we don't know really if it's blown or if it's working properly if you're passing a positive signal. So this is just all that we observe, what goes in and what comes out. And then so based on that, we can, here in this example are all possible explanations enumerated. And these are all things that could be true initial conditions that could lead to that observation of whether something is shorted or blown. And we can directly compute the prior probabilities of that. Now, to compute the posterior, is another story, and in general, Wolf kind of defers to, search techniques in which to do that. The sum of all these explanations, you might notice that explanations in this formalism also include the observation. And so the sum of these ends up being equal to the probability of the observation, the prior. So here's the setups. We have a set of facts. We have a set of hypotheses, and we have a function, PT, where we are assigning hypotheses to 0, 1, and of course this function for the assigning the probabilities has to conform to the disjoint declarations. So, so if you have G, which is your observation, an explanation of G is a set of D elements of set H prime, such that when you take the facts in union with them, you're going to entail G, and that there's no inconsistency when those are union together. So that's already very straightforward. It follows everything else that we've talked about. Now, what was interesting about this very old paper is he brings us up in a case that's actually very relevant to work that has come up almost 30 years later. So here what he's wanting to look at is we have a perceptual model. And he talks about maps. And he has two types of predicates. He has image predicates and scene predicates. And so given an object X, sigma of X is associated with the scene. And so we have all of these things here that maybe are sort of low-level things that could be concluded by something like a CNN, although he wasn't really thinking about it back then. We want to infer these items. And the reason why he has kind of these things written like bounds and closed, these are, he talks about this in terms of a map. So if you think of a map and he has this chi, which is just a crossing, we want to say, well, if we see a crossing, can we infer some of these features? Like if some part of, is there a road loop, or are some things inside and outside of each other, etc. So I'm going to use the laser pointer here on PowerPoint. So example rules that he gives. So if we have, so if I is a region, or I'm sorry, yeah, if there is a scene element of I that is an area, then we conclude I is a region. And then we can also look at this disjoint declaration that an area S could be water or it could be land, and these are the prior probabilities of that. Likewise, if there is the scene element in I and it's a linear feature, then we can conclude that I has a chain in it. And here we see different things that linear feature could be. It could be a river, it could be a road, and so on. So remember, it's the things in the body of the rule is what we're trying to conclude. The things in the head of the rule are just stuff that was recognized by the perceptual model. So we could think of other applications like, say, scene graphs, where it recognizes people doing different things and being related to each other, and we want to infer what's happening in the scene. And so the body of the rule would be what's happening in the scene, and the head would be these individual things. Because again, this is abduction. We're concluding which set of hypotheses causes those rules to fire. That's just the same thing I just said. So anyway, here's his example. So you have, I'll use the highlighter again. So C1 here is a chain. C2 is another chain. C2 is another chain. You have regions, R1 and R2, and so on. So all that's directly inferred by your perceptual model. Now here he came up with a bunch of explanations for this. So we could say that there is a road. There's a scene object that's a road associated with C1. There's another linear object that is also a road, and so forth. And because of the probabilistic information that was expressed in the disjoint declarations, he can compute the priors of these explanations as well. Now, notice here that we have these two different explanations where we're saying there is a river. And so we can also compute the probability of a river existing in that particular image. So it's the probability of a river given that there's an image, and that's pretty straightforward computation. Now, of course, enumerating all these explanations is expensive. If you want to actually compute the posteriors, which is actually, I think, a little more correct, that could also be an expensive operation. And then, of course, my favorite one is where do the rules come from? I mean, this looks like a lot of work to come up with all of these manually. So how do you do that? But anyway, that's where I'm going to leave it, because that's kind of sort of, I think why a lot of this work kind of died off after the 90s is many of these questions couldn't be answered. And with the exception of things that were very domain specific, like the geospatial abduction problem, you had a much more difficult time answering these. So if you think back to, you have the examples from the Poole paper, and then you have things like medical diagnosis, which was sort of the killer app of abduction in the 80s. You had, then you had some of my work with the geospatial abduction. Both of those cases, you have a very nice, solid body of domain knowledge that you can leverage to constrain those relationships between the hypotheses and the observations. When you get into something like, scene recognition, the question becomes, where do you get that? And that's a challenge. And this is, I think, where abductive learning becomes kind of interesting, because now we can start bringing to bear on, around the gaps that previously existed, bring some of these neural and perceptual techniques that have been developed over the past